Welcome to this session. In today's lesson, we will explore Learning Outcome 3, Understanding Populations and Samples. In statistics, it is often difficult to collect data from an entire population. Instead, researchers study a sample, which represents a smaller part of the population. This session introduces the relationship between populations and samples and explains why sampling is important for making reliable conclusions and predictions in data analysis and data science. A population includes every individual or item of interest in a study. Due to its size, collecting data from an entire population is often impractical. Instead, a sample, a smaller subset, is selected for analysis. This allows researchers to make inferences about the population. A well-chosen sample accurately represents the population, ensuring reliable results. Sampling saves time and resources by analyzing a smaller group. It makes large datasets manageable and allows for statistical inference. Sampling is essential for estimating population parameters. By using sample data, researchers predict or estimate population characteristics. Proper sampling ensures the validity of statistical conclusions. Random sampling gives every population member an equal chance of selection. Stratified sampling divides the population into strata, ensuring subgroup representation. Systematic sampling selects elements at regular intervals. Convenient sampling uses easily available data but may introduce bias. Each method serves different research needs and objectives. Sampling bias occurs when a sample does not represent the population accurately. This can lead to incorrect conclusions and unreliable results. Examples include surveying only online customers or excluding demographic groups. Bias reduces the reliability of statistical models. Ensuring representative samples is crucial for accurate data analysis. Understanding samples and populations is key in data science. Machine learning models rely on sample data for training. A non-representative sample can lead to inaccurate predictions. Sampling methods ensure data analysis results are valid and reliable. Proper sampling enhances the effectiveness of data science applications. Distribution measures describe how data values spread within a dataset. The mean, median, and mode provide insights into central tendency. The mean is sensitive to outliers, while the median is more stable. The mode identifies the most frequent value in a dataset. Comparing these measures helps understand data symmetry and skewness. Moments describe characteristics of a probability distribution. The first moment is the mean, representing the data center. The second moment, variance, indicates data spread. The third moment, skewness, measures distribution asymmetry. These moments help analysts interpret data behavior and guide statistical modeling. Kurtosis measures tail extremity and peakedness in a distribution. High kurtosis indicates more extreme values or outliers. Low kurtosis suggests fewer outliers and lighter tails. It helps assess the risk and variability of datasets. Understanding kurtosis aids in selecting appropriate statistical models. Tests determine if there are significant differences between means. A one-sample test compares a sample mean to a population mean. A two-sample test compares the means of two independent groups. Tests require normal distribution and independent observations. Results are interpreted using significance levels and p-values. The p-value indicates the probability of observing the test result under the null hypothesis. If the p-value is less than the significance level, the null hypothesis is rejected. This suggests the observed difference is statistically significant. A high p-value means failing to reject the null hypothesis. Understanding p-values is crucial for hypothesis testing. Mesokurtic distributions have kurtosis similar to the normal distribution. Leptokurtic distributions display heavier tails and more outliers. Platykurtic distributions have lighter tails and fewer extreme values. These types help classify distributions relative to the normal distribution. Analyzing kurtosis reveals distribution structure and risk characteristics. Understanding kurtosis helps assess risk and variability. It aids in identifying outliers and selecting statistical models. Mastering these concepts enhances data-driven decision-making. If you need any help, just WhatsApp 07484 361 688. Our team is always ready to assist. Thank you for your attention, and we look forward to seeing you in the next session.